Another one of the pipelining protocols is selective repeat, which is quite different from go back N in the sense that it provides buffer for receiving out of order packets and only necessitates the retransmission of packet which is in loss from the sender side. So it is quite going to be interesting when we look at the performance of selective repeat with regards to the buffering trade-off. Similar to go back N, we can also classify selective repeat in the wheat and rice analogy. Since selective repeat is not discarding all the packets, it is only requesting the packet retransmission which is in question by buffering them in the out of order buffer on the receiver side. It is more akin to rice in the wheat and rice analogy, where the older is considered to be better. This scenario with selective repeat, as you can see, buffers packet 3, packet 4 and packet 5, which are out of order because packet 2 in question is lost. When the timer times out for packet 2, it is retransmitted. On the receiving side, packet 2 is received. It is put back in order, and all these packets 2, 3, 4 and 5 are passed on to the upper layer, and the system goes back to its normal state. Similar to go back N, selective repeat also implements the same acknowledgement mechanism as go back N as a pipeline protocol, just because there is no difference in the absence of an error. So we see here that the efficiency is going to be the same, that is minimum of either 1 or N, which is the window size, times the transmission time for each packet divided by the total duration of the number of packets. But if there's an error, here selective repeat differs considerably from go back N. Here you see that the efficiency is only a difference of 100% minus the probability that a packet goes in error. So it means that if we compare it to the expression that we saw for go back N with errors, we'll see that there is a significant gain that we are achieving in selective repeat. But how can we possibly quantify this gain? We'll see that this gain can be quantified as a trade-off, because after all, selective repeat is necessitating more buffer on the receiving side now, and it is also doing an extra computational step of reordering these received packets once the lost packet is retransmitted and then passed on to the upper layer. So again, we have to see, is there any implication on the buffer size? So we need buffer at the sender. Why? Because when all the packets are transmitted, one of the packets is lost. We don't know which packet might get lost. So the retransmission request from the receiver side would appear on the sending side as a negative acknowledgement for the packet in loss. So we'll have to retransmit that packet. Likewise, on the receiver side, we don't know which packet might be received or it is not received at all. And if it is received, it might get received with error. So the buffer on the receiving side also has to accommodate all the incoming packets, but it can be slightly smaller than the maximum window size, because if the packet in loss is the last packet, then the only retransmission is going to take place for the last packet, and all the subsequent packets would be delivered to the upper layer, and there would be no requirement for reordering.